This is the third section of the Conic sections 2 chapter for FP1, and this is on eccentricity. Now, this isn't about people that behave in an unusual way. It's to do with like the shape of an ellipse. So we've come across ellipses already. Let's just draw a sketch of one. So remember, these are sketches, so these are not going to be fantastic. I'm sure there are other people that can draw ellipses far better than I can. So there's our ellipse there. Now, an ellipse can be defined just like a parabola in terms of a focus and a directrix. However, an ellipse has two foci and two directrices. Now, there's a focus here and here, okay, and those foci are at a distance of AE and minus AE. We'll talk about what E is in a moment. So these are the foci, so plural of focus. We've got two. With a parabola there was only one, and also a directrix here and a directrix here. I suppose maybe that needs to be moved over a bit so it's the same sort of distance away as the other one. So a directrix here, and just like the parabola, the ellipse here is going to be the loci of the foci and directrices. Okay, and the directrices, their equations are at x equals negative a over e, and one here at x equals a over e. Now you might be wondering to yourself, what's this e? Well, e is what we call the eccentricity of the ellipse. So e is the eccentricity of the ellipse. And basically, the bigger the value that e, the more sort of stretched out the ellipse is. We say it's more eccentric. Whereas if e is a smaller value, then it's going to be like close to the shape of a circle. And in fact, the eccentricity, its value is only ever going to be between 0 and 1. Now actually, if the eccentricity was 0, we wouldn't get an ellipse, we'd actually get a circle. And for an eccentricity which is greater than 1, our stretched out ellipse would actually turn into a parabola. So we're not interested in the circle or parabola, just those ellipses which are in between those. So the value of this eccentricity is always going to be, for an ellipse, between 0 and 1. Now, how do we find that eccentricity? Well, let's see. Actually, it's a ratio, and it's a ratio to do with this loci here. Now, with the parabola, with the loci, these two orange lines that I'm drawing would have been the same length, but with an ellipse, one of these is going to be a greater length than the other. So we're going to put some more labeling on this so we can sort of define the ratio of these lengths. So this ellipse is going to cross the x-axis at a and minus a. It's going to cross the y-axis at b and negative b. And actually, I'm going to move this to the other side. We're going to call the foci S here and S dash, like this. we'll call it a general point on the curve P. Maybe I should use a different color there. So let's go for purple. So general point here, that point we're going to call P. And then that perpendicular distance to the directrix here, this point here we're going to call M. Okay, and what we're interested in are the distances P to S or SP and P to M. So with a parabola, these here are the same length. With an ellipse, one of these is going to be longer than the other, and that's going to give us this ratio. Now, in the case where we've got an ellipse which sort of bulges out sideways like this, then we're going to have the length from P to M will be greater than the length P to S. Whereas if we had an ellipse which sort of was an ellipse this way, then we would find P to M, the length of P to M is less than P to S. I just want to correct something over here. When the eccentricity is equal to 1, it's a parabola. And when the eccentricity is greater than 1, that's when we get the hyperbola. Just want to correct that before I carry on. Now we're interested in this type here, where PM is greater than PS. And if we look at the ratio of PS to PM, for a particular ellipse, this is going to be constant. And this constant we call E, which is what we call the eccentricity of the ellipse, or the eccentricity. So it's just a ratio, and for a particular shape of ellipse, that value of E is going to be constant, so we can work out what that eccentricity is. We can use the equation of the ellipse to help us find that eccentricity. There's all sorts of different things we can do. So we've got an ellipse defined as a loci, but a loci where the distance between the foci and the loci and the loci and the directrix, they're not the same, they're different, and the ratio of that difference is called the eccentricity. So we can finish this off by saying, right, if we've got an ellipse with this equation, which we've come across before, we want one that bulges out sideways, like the one I highlighted, not one that sort of bulges out at the top and the bottom. And that will happen when A is greater than B, and that makes sense. It basically means that it's going to bulge out sideways more than it bulges out at the top. Okay, so we're going to be interested in those where A is greater than B. Then this eccentricity that we've talked about is going to be between 0 and 1. And what we're going to be proving in one of the first examples is that B squared, this same B squared we have at the bottom here under Y squared, is equal to A squared times by 1 minus E squared. Okay, show that for E between 0 and 1, okay, that the ellipse with focuses at AE0 and directrix at x equals A over E has equation x squared over A squared plus Y squared equals to 1. So we're going to draw a diagram that's going to basically help us do this question. Now I'm only going to draw part of the ellipse because there's going to be lots of different things we want to put on there. So I'm just going to pick out maybe this sort of, imagine that's like a quarter of the ellipse. Obviously it goes on around here like that, but just by looking at this point, this should be enough to help me work out what I need to do in this question. So here's my directrix, and I know that the directrix has equation x equals a over e. It's in the question, and we've got a focus at AE0, so let's put that in. So we'll mark in just this here, so that is going to be AE, that's its coordinate, and what we're going to be working out are these distances here, because we know that the ratio of those distances is going to give us E. So we'll label this as S. Normally we label a focus as S. This point here on the curve, we'll label that as P. And this point here that's perpendicular to the directrix we'll label as M. So these are normally the letters that we use for this. Now, because of the way this is and the types of ellipses we're looking at, we know that PS is going to be less than PM. So the eccentricity E is going to be given by PS over PM, that ratio. Okay, so this length divided by this length we know is going to give us the eccentricity. Now later on we're going to need these things squared, so we're just going to square the whole thing, and we're going to get E squared equals the length PS squared over the length PM squared, and we're doing that because we will need that in a moment. Now I'm going to form a right angle triangle just here, because I want to be able to find the length PS, and I can use Pythagoras to find that length. Now this point P, we know that its general coordinate is X, Y. Okay, so that means that this point here has coordinate X, and this point here has coordinate Y. So I can now use Pythagoras to find the length of PS. So PS, that hypotenuse of this triangle, is going to be this length squared, or the square root of this length squared, plus this length squared here. So what I will do, I'm not going to square root, so I'll say the length PS squared is equal to this length at the bottom squared. Now that length is X minus AE, so X minus AE squared, plus, and this length here is just Y, so plus Y squared. Now we want the length PM, and in fact we'll do the length PM squared. Now the length of PM is just the distance between this directrix and this point here X. So it's going to be AE, this coordinate, which is AE minus X, or sorry, A over E minus X. So now I'm going to write down an expression for the length PM squared, and PM squared is just going to be A over E minus X, so that's this distance here squared. Right, so now these two bits can go into my expression for E. So E squared is PS squared, which is this X minus AE all squared plus Y squared, over PM squared, which is this A over E minus X all squared. So the first thing we'll do is we'll times both sides by that denominator. So I'll have E squared A over E minus X all squared equals this X minus AE all squared plus Y squared. Now we'll expand both of those brackets. So I'll have E squared, then I'll have A over E all squared when it gets times by itself, then I'll minus 2 lots of a over e x, and then plus x squared. So if I expand that bracket, I'll do the same on the other side. So I'll have x squared minus 2 x, or 2aex, 2aex, then plus ae all squared, which is a squared e squared, and then plus y squared. Right, let's multiply out what we have on the left. So if I multiply everything by e squared, I'll just have a squared minus 2aex plus e squared x squared equals x squared minus 2aex plus a squared e squared plus y squared. Now you'll see that these cancel out because I've got minus 2aex on both sides. And let's see what we can do to try and get this in the correct form now, because that's basically the last thing that we need to do, is to get it into the right form. So I'll have e squared x, so let's take away x squared from both sides, like this. So I'm going to bring the x and y's all together on one side. Minus y squared, and that's going to equal a squared e squared minus a squared. Now what I think I'm going to do is multiply everything by minus 1, because really I want the x squared and y squared to be positive. So x squared minus e squared x squared plus y squared equals a squared minus a squared e squared. Right, I can see I can do some factorising. So I'll have x squared, and then I'll have 1 minus e squared plus y squared equals, and if I factorise the other side, I can factorise a squared out. So I'll have a squared 1 minus e squared. So if I divide both sides by a squared 1 minus e squared, like this, I will have, my apologies for the phone ringing there. Right, so where did we get to? Yeah, x squared 1 minus e squared. So we can divide everything by a squared 1 minus e squared. So plus y squared over a squared 1 minus e squared equals 1. So that's looking promising. So obviously these are going to cancel out. Now you'll notice where you would have b squared, so we normally have b squared there, it's equal to a squared minus 1 minus e squared. And that was what we had on the very first slide, wasn't it? So this is the proof that shows us when it's written in the correct form, b squared equals a squared minus 1 minus e squared, which basically means if you know the value of a and you know the eccentricity, you can work out the value of b. Okay, so we want to find the foci of the ellipses with the following equations and give the equations of the directrices. So we know the ellipses, we're looking for the foci and the directrices, and then we want to sketch the ellipse. Now since we know that it's an ellipse, with an ellipse we know the following, that the foci of the ellipse are going to be at plus minus AE. The directrices, the equations of the directrices are going to be x equal to plus or minus a over e, and the relationship between a, b and e is b squared equals a squared times by 1 minus e squared. So we know all of this to be true if it's an ellipse, so we can use this to help us. And this is the case where b is greater than a, where a is greater than b, which is what I see in the first one. It's going to be slightly different for the second one, and we'll talk about that in a moment. So starting with part a squared equals 9, so a equals 3, b squared equals 4, so b equals 2, so we want to find e as well. So we have b squared equals a squared 1 minus e squared, so b squared is 4 equals a squared 9, and then 1 minus e squared. So we want to rearrange it to find e. So if we divide both sides by 9, we'll have 1 minus e squared equals 4 over 9. So from there, if we bring the e squared over to make it positive, or multiply both sides by -1, we'll have e squared equals 1 minus 4 over 9. E can only be positive, which means that e squared, or e, is going to be the square root of, I think we're left with 5 over 9. So it'll be root 5 over 3. Right, so now we've got all of that, we can do our sketch. So we'll do our ellipse. It bulges out at the sides like this. Not the greatest ellipse in the world, but got the right shape, that's the important thing. We'll put the coordinates where it crosses the axes. So it's going to be a3 minus 3, b2 and minus 2. We're going to have the foci in here somewhere. So let's just do one there and one there. Okay, so we know that the coordinates of those are a, e, 0. So we're now going to work out a times e. So that's going to be 3 times by. So we'll put a, e equals 3 times by root 5 over 3, which is just root 5. So the coordinate here, I'll squeeze it in, is root 5, 0, which means over here, this is going to be minus root 5, 0. Now the each of the directrices, so one here and one here, let's make that a bit longer so I can do some working. Now for this, remember the equation of the directrix, each directrix is x equals a over e. Okay, so a over e is going to equal 3 over, or 3 divided by e, which is root 5 over 3, root 5 over 3. So that is 9 root 5 over 5 using the calculator, or 9 root 5 over 5. So I can now write the equations down as x equals 9 root 5 over 5. I'm guessing you could write this instead as 9 over root 5 if you don't rationalise the denominator. And this one is x equals negative 9 root 5 over 5. Okay, so that's part A done. So the important thing for the sketch is getting the right shape, the right places where it crosses the axis, the coordinates of the foci, and the equations of each directrix. Okay, now when we do part B, so let's start by working out A and B. So A squared is 16, so A is 4, and then B squared is 25, which means that B is 5. Now, what you notice here is that B is greater than A. Okay, B is greater than A. So let's just talk a little bit about that before we move on. So when B is greater than A, if we were to draw or sketch that ellipse, it would look like this. It would bulge from top to bottom. The foci would be on the y-axis, and the directrix, they would be horizontal, or each directrix would be horizontal. So that means some of the stuff we have is going to change. So if I look at the stuff that I highlighted in the cloud earlier, there are going to be some differences. So the first difference, when B is greater than A, what will happen? Well, the foci will be at plus and minus BE, not AE anymore, but BE. The directrices, whereas they were at x equals plus or minus A over E, now they're going to be y equals plus or minus B over E. And the relationship that we had that linked A, B and E, which was B squared equals A squared times by 1 minus E squared, that now becomes A squared equals B squared 1 minus E squared. So can you see what's happened is everywhere we had an A before, it becomes a B. So that A becomes a B, this A becomes a B, and the A and the B, they swap over. And also everywhere I had X before, it becomes Y. So if we wanted to summarize that, we could say something like this. We've got B greater than A. Then what we do is we swap A and B, swap over A and B, and then the other thing we do is to swap X for Y. Swap X for Y. So just be aware of that when you notice that B is greater than A. Yeah. So we need to take a little bit more care now when we sketch this ellipse. So the first thing we're going to do is to work out E. So the relationship is slightly different this time. So it's going to be A squared, which is 16, equals B squared, which is going to be 25, times by 1 minus E squared. So if I divide both sides by 25, I will get 1 minus E squared equals 16 over 25. If I then rearrange that to make E squared the subject, so I will end up with 1 minus 16 over 25, which is 9 over 25. So square rooting that, 9 over 25 is just going to give us 3 over 5, so 3/5. Right, so now we're ready to sketch. So we probably need to give ourselves a bit more space in the vertical direction, because our ellipse is going to be going like this with foci here. Let's move that up a bit, probably closer towards the edge than the middle, but it doesn't matter as long as we get the right values there. And our directrices now going like this. Okay, start with the first foci here. So the foci are going to be at plus or minus B over E. So B is 5. So B over E is going to be 5 divided by E, which is 3/5. Sorry, that's for the directrix, isn't it? B divided by E. It's B times by E. Sorry about that. So BE, I've got it written down up there, but I did the wrong thing. So B times by E is going to be 5 times by 3/5, which is just 3. So the coordinates of this top focus here is going to be 0, 3, and the one at the bottom is going to be 0, -3. So remember those X and Y swap around. And I'll do the same for the directrix. So I'll get this right. So it's Y equals, for the top one, B over E. So B divided by E is going to be 5 divided by, so I'll get it right this time, 5 divided by 3/5. Okay, and if I do 5 divided by 3/5, done it on my calculator already, that's 25 over 3, which then I can use to write the equation of each directrix. Now it's Y equals this time, so Y equals 25 over 3 for the top one, and Y equals -25 over 3 for the bottom one. So I think we've got everything that we need there. The coordinates of each focus, the equations of the directrix are, and we need to mark where it crosses the axis as well. I almost missed that out. So it's still going to be these values of A and B. So 4 minus 4, but now more, or bulging more in the other direction. So 5, whoops, and -5 here. Okay, so we've got an ellipse with this equation here, general equation of an ellipse. It's got foci at the standard points that we'd expect them to, and show that if P is any point on the ellipse, then if we add these distances together, it equals to A. So I'm going to tackle this question like I do lots of questions by starting with a sketch of my ellipse. So like this, I'm going to put on both my directrices on there, like that, and it's marking the points that we know. So let's put in the coordinates of each foci which we've been given. So these are, well, if I just write AE there, just write the x coordinate, and here minus AE, then if this is an ellipse, then it must be that each of these directrices here is x equals A over E here, and this one x equals -A over E. Now P is just a general point on the curve, so let's mark it here, and we'll call that point P. Now this is to do with distances, isn't it, between each foci and a point on the curve. Now this focus here, the one with positive coordinates, we'll call S, and this one S dash. So this is the distance PS. Actually, let's use a different color. Let's use green. So this is the distance PS here, and this is going to be the distance to the point on the directrix. Now we call that M, don't we? That perpendicular distance there. Now for the other point, that's going to be, let's use a different color. That's going to be a distance from P to that point, but then this is going to be the distance to this directrix, okay, which is going to be M dash. So it's important to note that each focus has its own directrix. Yeah, so this focus goes with this directrix, this focus, this distance is going to be this directrix over here. Right, so let's start off with the definition of the eccentricity, which is the distance from the focus to the curve, which is going to be PS, on the one on the right hand side, divided by the distance from the point on the curve to the directrix PM, is going to be equal to E. So I can rearrange that and write PS equals EPM. Now I can do the same with the other focus point, that's P to S dash. That divided by P to M dash also equals E. So that will be PS dash equals EPM dash. Now basically what we want to do, we want to eliminate this PM from both the equations, or actually, or PM from one and PM dash from the other. So the first thing we're going to do, let's have a look at what the length PM is. Okay, so let me add in the coordinates of this point here, P, which is XY, which means that this point here has coordinate X, and this point here has coordinate Y. Okay, actually it won't be there, it's going to be slightly below, isn't it? Yeah, so that will be where my Y is there. Now PM is the distance from here to here, which is the difference between this X coordinate and this X coordinate, which is going to be A over E minus A. So the distance from P to M is A over E minus X. Now we're going to do the same to find this distance here, P to M dash. Now the distance from P to M dash is going to be this distance here plus this distance. Now this distance here is basically A over E. That distance is A over E. Then add X plus X. So the distance from P to M dash is A over E plus X. So we can write P M dash equals A over E plus X. Right, so using the expressions I've got up here, I can now write PS equal to EPM, or E A over E minus X, which means that PS equals, if you times it all by E, A minus EX. I'll do the same with PS dash. So PS dash equals E PM dash, so E times by A over E plus X. So PS dash equals A plus EX. So if I now work out PS plus PS dash, that's A minus EX plus A plus EX, and that just gives you 2A, because obviously these are going to cancel out. So you get the result as required. Okay, so here it says show for E greater than 1. So when E is greater than 1, we end up with this hyperbola. Okay, and we're told the coordinates of where each focus is and the equation of the directrices, and we want to show that this hyperbola has this equation. Right, so let's sketch a hyperbola, and just like previous ones, this is about distances between the focus and a general point on the curve, and a general point on the curve and a directrix. So let's just maybe look at no, let's put something like this in. Okay, so we need to put a directrix in as well. So I'll put this here, and we're going to have a focus in here, and this focus, its coordinate is going to be AE. The directrix is going to have equation A over E. We'll take a general point on the curve, and that's going to, we call that P, and it has coordinates x, y. The focus we'll call point S, and the perpendicular distance from that point to the directrix we are going to call M. So these are the normal letters that we use. Okay, and what we're interested in are the distance P to S and P to M, because that ratio PS over PM is going to give us E, the eccentricity. So let's start by writing that that ratio that we're just talking about, PS over PM equals E. Now, since we're going to be talking about distances, we're going to square this. So we'll have PS squared over PM squared equals E squared. Right, so let's have a look first of all at the distance P to S. Now, P to S is this sloping distance here, which we can use Pythagoras to help us work out the length. So if I put in light blue these lengths here, this length here is just y, because that goes from the x-axis up to that point, general point there. And this length here, well, this coordinate here, that value is x. So the distance, that distance there is x minus AE. So the length PS squared is equal to, that length at the bottom is x minus AE all squared plus y squared. Then looking at PM, or PM squared, this length PM you'll get by doing the distance between this point x, because x is just underneath P, and this point here, which is going to have x coordinate A over E. So the distance from P to M is x minus A over E. So PM squared is x minus A over E all squared. So write that down. So PM squared, distance from P to M squared, is x minus A over E all squared. Now, if I rearrange this, I can say that PS squared equals E squared times by PM squared. So I can put this all together. So PS is x minus AE all squared plus y squared equals E squared times by PM squared, which is going to be this, x minus A over E all squared. So let's expand the brackets, simplify it, and see where we go from there. Right, so expanding the first sets of brackets, I'll get x squared, and then I'll have minus 2AEx plus AE all squared, which is going to be A squared, E squared plus Y squared. Then on the other side, I'll have E squared times by, now the brackets, I will get x squared, then minus 2AE, sorry, that should be 2 times by A over E x, then plus A over E all squared, which is A squared over E squared. Let's multiply out the brackets on the right hand side. That will give us E squared x squared. Then we'll have minus 2E x, if you times that by E squared, plus A squared. Oh, whoops, I missed the A out. So E A, or AE x, then plus a squared. Now we've got this same term on both sides, 2aex, so they can cancel out. So that will just leave us x squared plus a squared e squared y plus y squared equals e squared x squared plus a squared. Now what we're going to do is we're going to bring the x terms all to the same side. So you've got x squared minus e squared x squared plus y squared, and then we'll move the a squared e squared to the other side, so minus a squared e squared. Now we do that so that we can factorize. I can factorize out the x squared on the left, so I'll have 1 minus e squared in brackets, then plus y squared, and then on the other side I will factorize out the a squared, so I've got a squared and then 1 minus e squared. Now you'll notice at the moment I've got a plus here, and I want it to be a minus because the equation has a minus in it. So what I'm going to do is multiply everything by -1. Now when I multiply everything by -1, what happens with the brackets is that what's in the brackets reverses. So it's no longer 1 minus e squared, it's e squared minus 1, then minus y squared. And the same thing happens on the other side. If I multiply that by -1 or -1, I'll get e squared minus 1. Right, so from here, I will divide both sides by a squared e squared minus 1. So I will have this x squared e squared minus 1 over a squared e squared minus 1 minus y squared over a squared e squared minus 1 equals, well, it'll just be 1. Now what will happen is that these will cancel out, just leaving x squared over a squared minus y squared over a squared e squared minus 1 equals 1. So you can see if this is going to be a hyperbola, we can see this is where b squared, the thing that's underneath the y squared, equals a squared e squared minus 1. Right, for this one, find foci for the following hyperbolas. In each case, sketch the hyperbola and show the directrices. So foci, directrices, sketch. So let's start with A, and probably in fact let's start with what we know about the hyperbolas, what their general features are. So there's going to be foci at these points, plus or minus AE0. There's going to be directrices when we have x equals plus or minus a over e, and also we're going to have b squared equals a squared e squared minus 1. So we'll start by finding a and b. A is for part A 3, b is 2, so we'll use that to find e. So 4 equals, so b squared equals a squared e squared minus 1. So that will give me 4 over 9 equals e squared minus 1, which will give me e equal to 4 over 9 plus 1, which would be like adding 9 over 9, 13 over 9, and if we square root that, we'll get root 13 over 3. Okay, let's work out the foci and directrices before we sketch it. So the foci are going to be at A times E, and that's going to be 3 times by root 13 over 3, so at plus or minus root 13, and with the directrices they're going to be where x is equal to plus or minus a over e. So let's work out a over e, so that's 3 divided by root 13 over 3, which is the same as 3 times by 3 over root 13, which is going to be 9 over root 13. Right, so now let's sketch. So it's probably easier to work out these values before we stick them on the graph. So hyperbola, like this. Foci at root 13, 0, and negative root 13, 0. Directrices at x equals 9 over root 13 and x equals negative over 9 root 13. And the hyperbola crosses the axis at a and minus a, so it crosses at 3 and negative 3. Okay, let's do the same type of thing for b. So for b, a equals 4 and b equals 5. So we're going to use that again to work out what e is. So b squared 25 equals a squared 16, e squared minus 1. So that means that 25 over 16 is going to equal e squared minus 1. So e will equal, so you've got 25 over 16 plus 1, which is like 16 over 16. So that will give us 41 over 16, and square rooted will be root 41 over 4. So root 41 over 4 is the value of e. So let's have a look at where the foci are. So these are going to be at a times e. So that's going to be 4 times by root 41 over 4. So that's going to be foci at plus and minus root 41. And then for the directrices, they're at x equals plus or minus a over e. So let's work out a over e. So that's going to be 4 divided by root 41 over 4, which is the same as 4 times by 4 over root 41, which is going to be 16 over root 41. So that's going to give us where our directrices are going to be. Right, so the rest now is just sketching. So y-axis, x-axis, our hyperbolas here. Now they cross the axis, oh that could be a bit better. They cross the axis at a, which is 4, so I'll put that down. So negative 4, 4, foci here, and the foci, one at root 41, 0, and the other at negative root 41, 0. And then directrices at x equals 16 over root 41 and x equals negative put it over here, x equals negative 16 over root 41. Okay, so you should now be able to do exercise 3C on pages 73 to 74. There's going to be quite a lot of recaps. I'm going to pause it, write it all down, and then sort of go through it fairly quickly. So here you go, a recap of all of the bits that we've done here. The ellipse, where A is greater than B, that's the main focus. But just be aware of the ellipse where B is greater than A, and how those things swap around. The hyperbola here as well, and it probably would be worth mentioning actually what E is, this eccentricity, so I'll just write a note on that. So just a little note at the top here, where E is the eccentricity, and it's equal to this ratio of the distance from focus to a general point on the curve, and from that general point divided by a general point to the directrix. And often you can use this to prove the equation for an ellipse on hyperbola, or actually any type of conic section. We'll use this where it involves the eccentricity. So that's the distance from the focus to a point on a curve. So we'll just put that down. So S is the focus, P would be a point on the curve, so that's going to be XY, and M is going to be that's perpendicular distance to the matrix, or the not matrix, the directrix. So distance, not distance to directrix, but just basically the directrix.